So next Monday, this is, I'm going to announce again, is no lecture, but if you do show up, it will be a tutoring session, and there will be a pro-section student here to help you with putting the information together. The student is not here to give you answers. The student is here to help you get yourself organized and to make sure that you're not thinking incorrectly about how certain things function, and to help make sure you're on the right path. So it'll be from noon to about 12:45. If you're interested, you're more than welcome to come, whether you're Monday, Wednesday, Friday, Tuesday, Thursday, or internet students. With that said, our exam is a week from today, and Monday, Wednesday, Friday is also able to take their exam with the Tuesday, Thursday class, and vice versa, because our classes are now small enough to where it doesn't matter which section you take your exam with. So remember, noon Friday or 4 p.m. Thursday. You just have more time on the 4 p.m. Thursday to take the exam. It's an hour and 15 minutes, and it's still 50 minutes for the Friday. Okay. Parathyroid glands. They are called parathyroid glands because they're around the thyroid. Actually, they're embedded in the thyroid gland. They are so small that you cannot actually identify them on a living specimen or on a cadaveric specimen. And so the only way they actually can identify them to even surgically remove them so that they could actually put them in other areas of the human body so that they can maintain calcium homeostasis, because that's what our parathyroid glands are supremely needed for, calcium homeostasis. We talked about calcitonin previously as one of the hormones that is released from the thyroid gland itself, but calcitonin doesn't play a role in our true calcium homeostasis. It's just a very minor player and more important for children and less important for us. Parathyroid glands, however, are supremely important for our calcium homeostasis because they produce a hormone called parathyroid hormone, abbreviated PTH, and I'll write that down in just a moment. There's typically four. They're typically on the back side of our thyroid gland, and whenever somebody has to have their thyroid gland removed, do you guys have any idea why we would actually remove a thyroid gland in an individual? Cancer. Cancer is the #1 reason for removal of the thyroid gland. Also, if a person has been in an area where there is no iodine essentially in their diet, what do you suppose their true thyroid hormone levels are like if there's no iodine in an individual's diet? They don't have thyroid hormone circulating around. They're hypothyroid. And the reason they're hypothyroid is thyroid hormone needs iodine to be active. Remember, the inactive form is stored in that colloid. And then when TSH tells the thyroid gland we need thyroid hormone, because that's what TSH does, so the thyroid gland can make more thyroid hormone, but what it does is it's going to take the stored form first, and it's going to iodinate it, and then it's going to put it in circulation so it can circulate around to the tissues for proper use. So cancer is one reason to remove a thyroid gland, and a bad goiter, because the problem with a goiter is once a goiter occurs, you can't reduce its size. And so if you've ever seen some of those rather impressive goiters, that's where the thyroid gland is huge. You see a big bulge in the inferior aspect of a person's neck anteriorly, and that's the thyroid gland has enlarged so much because it is full of colloid. You guys follow me with that? It's making the thyroid hormone precursor and keeps making more and more and more and more, but cannot actually use thyroid hormone because they're from an area where iodine level's low. That is actually the main reason why our salt is iodinated. So iodized salt, that's the reason why we have iodized salt. So that we used to actually have goiter problems and hypothyroid problems in the United States. But that was a long time ago until they realized iodine is a key component for the formation of active hormone. So parathyroid glands are embedded in the thyroid gland. Can't see them, and so if a surgeon has to remove the thyroid gland, they will remove the parathyroid glands, which will totally screw up a person's calcium homeostasis. So in order to not do that, they'll inject a little dye that is designed to actually be concentrated in the parathyroid glands, and they can actually see then these little now colored parathyroid glands, pluck them out and put them inside the mediastinal area. And they actually can survive fairly well if you just put them in an area where there's a decent vascularity associated with it. So it's kind of neat that these guys, as small as they are, doesn't matter where you put them. As long as there's a blood supply close by that they can hook up to, they will survive and be happy and take care of your calcium homeostasis. So indeed, calcium homeostasis is what they are desired, what they're needed for. Now, the calcium homeostasis comes about because parathyroid hormone, PTH, that's how it's abbreviated, parathyroid hormone, is going to actually increase osteoclast activity. Well, osteoclasts do what? Break down bone, and when you break down bone, you're going to release calcium into the bloodstream. So some women with osteoporosis have actually a parathyroid hormone problem. Because you could see if you had unregulated high parathyroid hormone levels, you would actually have osteoclast activity being high, causing osteoporosis. So that's what parathyroid hormone does, increase osteoclast activity, therefore increasing blood calcium level. Now, why would you release parathyroid hormone in the first place then? Blood calcium level is low. When blood calcium level gets up to normal, what happens to parathyroid hormone release? Stops. Typical classical negative feedback mechanism. Is this hormonal, humoral, or neural in its release? Humoral, because it's a ion, it's something in the humors which stimulate its release, correct? So as you go through your notes here, don't forget that you should be thinking about hormonal, humoral, or neural is the stimulus mechanism for the release of any of these hormones that we're actually talking about. So we increase osteoclast activity, which will then increase calcium levels, blood calcium levels. The cells of the parathyroid gland are called chief cells because they are the chief cell of that gland. As you take a look, all these cells look alike, and they all look, and it's just full of these guys, so they were called chief cells. They also have another name. You can call them principal cells. Or you can call them parathyroid cells. So they're called all these different names, and it depends upon which test you have and which book you're reading. So I need to make sure that you realize that these are all the possible names that you can see of the predominant cell, which is producing parathyroid hormone. Let's take a look at this picture over here, and it's full of chief cells. So the parathyroid gland is right embedded in the thyroid gland, and it's always easy to identify the parathyroid when you have thyroid right next to it, correct? Because that's the only thing that's associated with the thyroid gland. So it's hard to initially recognize parathyroid gland tissue unless you go, boy, all these cells look the same, and they're all small, and it looks like it's dark, it's all full of nuclei. Now that helps a little bit, but not enough, because when we get into lymphoid tissue looks just like this too. So you have to have some thyroid gland close by in order to be able to identify this as parathyroid. There is a cell in the parathyroid gland that we don't know the function of, but it's there, and so you have to be able to identify that too, and that's the guy called the oxyphil cell. Take a look at the leader lines going to the oxyphil cells, and how would you say that this cell is different from a chief cell? Cytoplasm. They have a lot more cytoplasm than a chief cell does, so the nuclei aren't so crowded around them, correct? And that's how you actually take a look at this. So that's what histology is meant to teach you, is you take a look at something and say, what is different from this cell and this cell? What are their differences? And that's how you start to learn how to identify various tissues. So the oxyphil cell, we don't know what it does still. It's an unknown function, but it's still a component of the parathyroid glands. Now, we're going to increase blood calcium when we have parathyroid hormone released, and then calcium levels will get to normal, and then parathyroid hormone levels will actually go down. Remember, most important hormone for adult calcium homeostasis. It works in kids too, so this will come into play when kids are not getting enough dairy in their diet and things along that line, or foods rich in calcium, so the parathyroid hormone levels will be up also in those individuals, trying to make sure that they have adequate calcium in the bloodstream, because as we are going to learn, it's not just sodium that's an important electrolyte in normal functioning of our cells. Calcium is a very important electrolyte in function for our heart. Let's go to the next gland, endocrine gland in our list here, the adrenal glands, which are also called our suprarenal glands. And our kidneys are cushioned in a fat capsule. So they are surrounded by a whole bunch of fat. And the adrenal glands are also hanging out with the kidneys. They're literally sitting on the superior pole of the kidney, on the superior aspect, and they are also encased in fat. The interesting thing about the adrenal glands, they look just like the fatty tissue that's around the kidney visually, but when you put your hands on them, fat is real smushable, right? If you guys remember your cat fat, you pinch it in your fingers and, you can get right next to one another. You just pinch the fat out of the way. Well, a gland is not so smushable. And so it requires not just visualization, but actual tactile recognition that you actually have a gland that's actually part of that fatty capsule. The other thing about the adrenal glands, they're very vascularized. They're very well hooked up to the bloodstream, because remember, these are actually glands, the adrenal medulla, that releases adrenaline into our bloodstream. And so they have a lot of vascularity also associated with them. With our adrenal glands, we have two main areas. One area called the cortex, which is always meant to be outer, and the other, the medullary area, which is always meant to be inner. Remember, we have hair cortex and hair medullary area. So always cortex is outer, medullary area is inner. And of the cortex, we have 3 layers that will produce very specific hormones. But as you make your histology drawings for the adrenal gland and the adrenal cortex and stuff like that, it's not that difficult to do. You have to make your capsule, which is always the outer aspect, and then you make a very small area called the zona glomerulosa, and those cells kind of are clustered together. And so I would be drawing kind of these weird looking clusters, and of course put in some nuclei so you recognize that it's supposed to be a clustering of cells. You guys take so long to draw your pictures, it's really kind of interesting. And then I would make cords, because then the next layer is the zona fasciculata. And put a bunch of cells hanging out in the cords. But I would create that kind of a linear look to things to help as my guide as I make this. And then, of course, I put nuclei inside my cells. But that's the thing for fasciculata. It's a fascicles, it's a linear arrangement of cells. And then zona reticularis is a network look to it. And so I'd make sure that my cells follow along in a network type of a pattern. So it's not linear, it's not curly-cued or glomerular-like. It's lacy-like. And then you'd make sure that the zona glomerulosa is the thinnest, the zona fasciculata is the thickest as far as depth into the gland, and then zona reticularis is less thick. And then you have your medullary area, and one of the things to make sure that you do is that the coloration is definitely different in the medullary area, and we'll have a lot of blood vessels in that. So that's what that is showing you. Those red things there are actual blood vessels. So make sure in your histology drawing you actually have those items there to help you identify that. Descriptor-wise, zona glomerulosa produces a hormone, or produces hormones that have a broad categorical name called mineralocorticoids, because they control minerals or ions. So mineralocorticoids. The main mineralocorticoid from the zona glomerulosa is aldosterone. Aldosterone, when it is released, will cause our kidneys to retain sodium and excrete potassium. So these are both cations, and so we can do almost a one-for-one exchange. And the stimulus for aldosterone release is elevated blood potassium. What's a good source of potassium in your diet? Bananas. Most everybody knows bananas actually is a pretty decent source of potassium. So are avocados, evidently. But bananas are a good source of potassium. So when you eat a banana, your blood potassium level goes up. What else goes up then? Aldosterone goes up. And so aldosterone says your blood potassium level is high. We need to get it back down to normal. And so I'm going to cause you to put potassium in your urine. And in doing this, I have to retain sodium. Well, what happens when we retain sodium? We always retain water. So wherever sodium goes, water goes too. This is a very classic osmotic event. So the release of aldosterone will cause more fluid retention from the kidneys for you with that sodium. Now, ACTH, remember adrenocorticotropic hormone, is supposed to stimulate the adrenal cortex to release their hormones. ACTH is not a big player here. We will talk about, there is always an exception, but I want you to realize classical ACTH levels will not affect aldosterone release. It is actually a mineralocorticoid that will respond to what? Hormonal, humoral, or neural stimulus to make it release aldosterone. Humoral. So the others in zona fasciculata and reticularis are going to be hormonal, because ACTH is going to be the hormone they tell them to release their hormone, but except for this zona glomerulosa. That's the main thing about the zona glomerulosa that I want to talk about right now. We'll get a little bit more detail about aldosterone when we talk about the kidneys, because obviously this has a big impact on our kidneys. Zona fasciculata, the fascicles, the linear arrangement of cells. The main hormone category from this area of our adrenal gland is called glucocorticoids. And gluco, so that's something to realize. They help us to make glucose. So glucocorticoids help us to make glucose. We consider this a metabolic hormone because typically we need glucose for cellular metabolism, correct, to make ATP. So it's kind of the food or the fuel for our cells. The main glucocorticoid that is released by the zona fasciculata is called cortisol. And sometimes you'll hear it called hydrocortisone. So cortisol. This causes you to create new glucose from fats and proteins or amino acids. So we have to break down fats and we have to break down proteins in order to get the building blocks to make glucose for us. So this is something that we need when we're actually under a lot of stress. So people will talk about stress causes their cortisol levels to go up. Absolutely, indeed it does, as we actually create these fuels for that. Now, cortisol in excess is also anti-inflammatory and anti-immune. And we do give cortisol to people in excess over what is called normal physiological levels. Why do we do that to people? Why do we give them a medicine that will cause anti-inflammatory or anti-immune effects for them? Certain inflammatory conditions, really bad rheumatoid arthritis flare, right? And then anti-immune. What about rejection of organ transplants? One of the things that they'll give them is a form of cortisol. What is the most common? Does anybody know what the most common cortisol form that is taken by people orally? Prednisone. You may have heard of prednisone. So prednisone is what we actually administer to people, which is a form of cortisol that's above physiologic levels, the normal levels the body creates, to suppress the inflammation or suppress the immune response. Now, you have side effects too when you take medications in excessively high doses. And so nobody wants to be on these for very long because this can also cause thinning of the skin, cataracts, diabetes, weight gain, hormonal imbalances, bleeding problems for women from their menses, all kinds of things. So a lot of these things are taken by some people for long term because that's the only thing that works for them. Otherwise, their life is obviously more miserable than the side effects that can actually occur for those individuals. So that's the story about zona fasciculata and cortisol. Now we're going in deeper and we're going into the zona reticularis, and this one is responsible for secreting a group of hormones that fit the category of gonadocorticoids. So they're going to actually be something that we would associate with the gonads: testosterone, estrogen, progesterone. And actually the main hormone or gonadocorticoid from the zona reticularis is called androgens, and they are weak androgens that they actually make. Weak androgens. Androgens are typically considered male hormones. This is something that when you hit puberty and you get increased acne and all that kind of stuff, the androgen levels are typically high on that. So, but it isn't. It's a male hormone and it is a female hormone. So all men and women have a certain androgen level that is from the zona reticularis. The interesting thing is that at the target tissue, these androgens are converted into testosterone or estrogen. So these weak androgens will circulate around, get to their target tissue, and before they are actually allowed to do their function, the target tissue will convert them to the hormone that is best for their activity. What's really interesting is that these androgens, in order to actually have nice, healthy bone formation, we all require estrogen. So both sexes have estrogen and testosterone associated in their blood stream. However, for women, testosterone is very low. In men, it's very high. And in men, estrogen is very low. And in women, it's very high. And those variations in levels will affect secondary sex characteristics as well as fertility. So that's zona reticularis. Now let's go to the adrenal medulla, which is responsible for releasing catecholamines. 75% of the catecholamines are epinephrine, and 25% is norepinephrine. Epinephrine has a profound effect on the heart and metabolism. Norepinephrine is a very potent vasoconstrictor. So it'll definitely cause blood pressure to go up with vasoconstriction. So epinephrine, it will cause the heart to increase its rate as well as its force of contraction, and it will cause metabolic effects to where we'll have more actual glucose in the bloodstream to actually feed our cells that are actually hyped up at a higher metabolic rate. So those are the catecholamines from the adrenal medulla. Now let's go to the pancreas. And the area that we are interested in the pancreas are the pancreatic islets, also referred to as the islets of Langerhans. We have to tell you, remember I tell you all of these different names because when you're in academics, we'll use the more academic term, and when you're out in the field of medicine, they'll typically use the term that's been used for decades in the medical field, and Langerhans was the guy who obviously identified these. And when they talk about the endocrine function of the pancreas, they'll talk about islets of Langerhans if they're from the older school. If they're from a newer or younger school, they might just say pancreatic islets, and so I give you the information so that whenever they say one or the other, you know exactly what they're talking about. Our pancreatic islets are embedded in the pancreas in all of this acinar tissue, A-C-I-N-A-R, acinar tissue. That's the bulk of the pancreas, is acinar tissue. That's where the exocrine digestive enzymes are created and then emptied into what's called a pancreatic duct, which we'll learn will empty into our duodenum to help us with digestion. But this is a special stain just for the pancreatic islet to help us see the distinction between the two cell types, the alpha cells and the beta cells. The beta cells are the predominant cell type, and so those are the ones with the pale staining slightly blue cytoplasm that we see here. And then the alpha cells are the ones that have the reddish pinkish cytoplasm. And so I hope you can appreciate that we have more beta cells in this pancreatic islet than we do alpha cells. And that is because our beta cells are the ones that are responsible for producing insulin. And insulin is designed to actually decrease blood glucose levels. The important thing about our beta cells is that insulin is a 51 amino acid protein that affects almost all of our cells. So basically, and I haven't told you which cell it doesn't affect, so you don't have to worry about it. It affects almost all of our cells to allow glucose into the cell. So these little pale blue guys all in this little strand here are all, well, it's not doing a very good job, but are all, I can't seem to circle them, are all beta cells. So you should be able to look in that and figure out the beta cells from the alpha cells. The alpha cells also release a hormone, and that hormone is glucagon. And glucagon is designed to increase blood glucose, whereas insulin is designed to decrease blood glucose. What's interesting, glucagon targets primarily the liver. And it will cause glycogen breakdown. Glycogen is a storage form of glucose. And therefore glucose release into the bloodstream. Why would we want to do that? Why would we actually want to dump glucose into the bloodstream? Hypoglycemia, absolutely. And and this liver is the one that's going to be releasing all this glucose into the bloodstream because it's a great organ. It stores a bunch of glucose and glycogen and does all sort of metabolic processing for you. But when are your blood glucoses ever low? Because this is a normal physiology aspect. When are your blood glucoses ever low? Starvation, yes, absolutely. We'd have a lot of glucagon being released then. Sleeping, we sleep. And finally, we don't eat. So all throughout the daytime, you can nosh on anything you like, right? There's all kinds of food out there for you to actually enjoy. But when you're sleeping, you can't eat, and that's what the liver does. The liver maintains a nice glucose homeostasis so that we have adequate glucose to supply all of our cells while we're sleeping. And then when we eat, what happens to our glucagon levels? Goes down. What happens to our insulin levels? Goes up. Now, because I tell you that we have glucose being put into the bloodstream so we can eat, will glucagon and insulin be released at the same time? Think about it. Blood glucose levels low? Why? Why did your blood glucose level go down in the first place? Because of insulin, right? And why is insulin being released? Because glucose levels were high, and why do you need glucose? You have to feed your cells. Do you have to feed your cells all the time? Absolutely, yes. You may eat at different times of the day, but your cells need a constant diet, actually. So if you want your cells to do the things that they're supposed to do 24 hours a day, you need to feed them 24 hours a day. So your glucose level only goes down because insulin was there. Because if insulin's not there, what happens to your blood glucose level? Think about it. Goes up. But you're not eating. Will your glucose levels still go up if you don't have any insulin in your system? Which will bring us down to one of our diabetes stories. Yes, because one of the things that's important, your cells need glucose 24/7. The only way glucose gets into your cells is because of insulin. So your blood glucose level is down, glucagon is released to make blood glucose levels go up, so therefore glucose can go into your cells. So you can have glucagon and insulin being released at the same time. Can you follow me with this? Because you need glucose to feed your cells. In order for glucose to go in your cells, you need insulin. So they work together, but when glucose levels are high, you don't need glucagon anymore, correct? You need insulin. And when glucose levels are low, you need glucagon. So what kind of feedback mechanism do we have with both of our alpha cells and our beta cells? Is it positive feedback or negative feedback? There you go. There's a brave soul in there. What's wrong with you guys? It's Friday. It would be like a TGIF for you guys. And you act like, oh, we got another day of this stuff. So yes, these are both negative feedback. It's a balancing act. Can you guys follow how our endocrine system is always balancing hormonal levels and activities of various cells and what we need to do? So this is indeed a negative feedback for both of these systems. So now let's go into dysfunction of our endocrine portion of our pancreas. And that's diabetes or diabetes mellitus. Type 1 diabetes used to be called insulin-dependent diabetes mellitus or juvenile onset. And so it was IDDM, insulin-dependent diabetes mellitus. And they called it juvenile onset because you weren't born with it. You acquired it for some reason. And it means insulin dependent because you no longer have insulin. If you no longer have insulin, you are no longer feeding your cells. Do you guys follow me with that? This is very basic. Insulin is required for glucose entry into your cells. So when we have type 1 diabetes, this phenomenon is due in over 90% of the cases, due to autoimmunity to which cell? To our beta cells. It's the beta cells which produce insulin. If you are autoimmune to your own beta cells, what will your immune system do to your beta cells? Off them, right? And if one survives, they'll kill it. And if another one survives, they'll kill it. And they'll keep killing your beta cells until they're all gone. So that means that your insulin level starts to drop, which then requires all your cells to upregulate. You guys remember all that stuff we talked about earlier? And so your body's trying to compensate for this overall insulin deficiency until there is no insulin anymore, which is what this autoimmune process will do. It will destroy the beta cells, which are responsible for secreting insulin into the bloodstream. And so when you get destruction of beta cells, what do we know about blood glucose now? It's high. And this is because glucose, even though we're swimming in a sea of it, glucose is unavailable. For our cellular use. And so your cells actually will be putting out all kinds of chemical messengers saying, I'm starving, I'm starving, I'm starving, I'm starving, feed me. And so that's one reason why a person who has this type of diabetes, their sugar, in spite of starvation, will continue to rise. And it continues to rise because we will break down a fuel source, which means an energy source, that is not glucose-based for our needs. And that other fuel source will be fatty acids. Do you guys remember the classic molecule that has 3 fatty acid chains hanging off of it? Triglycerides. And triglycerides are what we actually have in our little fat globules, right? Our fat cells are just full of triglycerides. So we will be breaking down triglycerides. In other words, we'll be going to the fat cells, we'll be pulling out triglycerides, and we'll break them down so that we have our fatty acids for cellular fuel use. And this will cause a lipemic blood or serum. Lipemic, I hope you follow the root word there, lipid. If you have somebody who is insulin-dependent diabetes and they're having some very serious problems, you draw their blood and you let it sit, and it will have a layer of cream on top. This layer of fat will literally settle out because we are using alternative sources for fuel, and the only way you can get that alternative source for fuel is to go in there and rob the fat bank. And you're going to rob that fat bank and you're going to put it into the bloodstream. So the blood will have TGs, triglycerides, and at the same time will have high cholesterols. So it's an interesting thing if you have a healthy person and things are actually pretty normal and they're looking pretty slender and trim and everything, and they have all of a sudden their cholesterol spiking up. That's us, and they say, I have a very healthy diet. Then they have some sort of metabolic process going on that could actually be a precursor to diabetes for them. So this is a hallmark of a diabetic individual. They can be as skinny as a rail because we have robbed all their fat from them. But the blood lipids will be very high and everything will be out of balance. And what's bad about having a bunch of triglycerides and cholesterol floating around in your bloodstream? What's bad about that? It's like sludge. You know how it layers out in that tube? Well, guess what it does when it gets in the teeny tiny blood vessels, which feed your organs? It fills it up with sludge, which means what about blood supply to your organs? poor. And that's why people with this type of diabetes have a tendency to lose their digits and their feet and all kinds of things related to this problem. So insulin-dependent diabetes mellitus is something to be taken very, very seriously because it has profound effects on an individual. The other problem is fatty acid metabolites. Build up and produce these fatty acid metabolites eventually are of the category called ketones. And the more ketones you get, which have an acid nature to them, you get this condition called ketoacidosis. And ketoacidosis is a really, really bad problem. People die from it. This will lead to the final topic in this chapter called cellular exhaustion. Ketoacidosis kills. And the only way you can help somebody with type 1 diabetes is to give them genetically engineered insulin. Do you guys know where genetically engineered insulin comes from? It comes from some GMOs, a genetically modified organism. They take E. coli, a little poopy bug. That's what I always associate E. coli with. Who does not associate E. coli with poop? We all do. Good. So they take E. coli and they take a gene from a human for insulin, and they insert it into E. coli. And the nice thing about E. coli, they rapidly multiply. And so you now have E. coli with human insulin gene, and their byproduct is human insulin. And so then you harvest the human insulin from them. Before we had this insulin, which is exactly identical to your insulin, we had to use insulin that we harvested from cows and pigs. So we had to use bovine and porcine insulin. And the problem with bovine and porcine insulin, it is not a 51 amino acid insulin. It's not exactly genetically identical to ours. And so those people back then who had to use those insulin, they would typically have to go up and up and up and up and up on their dose of insulin because that insulin was foreign. And your immune system is designed to recognize foreign material and take it out. So it's not supposed to be utilized by you or harm you because that's what your immune system says. Foreign stuff in you doesn't belong in you, has to be bad, so we take it out. And so in those days, people would have to really have very high doses of insulin because of their immune system taking out the insulin for them, unfortunately for them. With genetically engineered insulin, it is exactly the same as yours, and we don't have that problem, which is actually really, really nice. And so this is given not by mouth, this is given by injection. It's either with a little syringe, an insulin syringe, which is carefully calibrated, or with insulin pumps. And so people who are able to use insulin pumps can afford them and get some good ones, have a more productive or more normal life. Because previously you always had to check your blood sugar level to figure out what dosage range of insulin you would actually administer yourself for that day. So that's an interesting thing about insulin-dependent diabetes mellitus. Now let's talk about type 2 diabetes, which was called non-insulin dependent diabetes mellitus, or NIDDM. But now it's called T2D. Type 2 diabetes is what I see now in the literature a lot. They called it adult onset diabetes also in the past, but they can't do that anymore because there's too many juveniles now with type 2 diabetes. This is a problem that's brought about by our lifestyle. Type 2 diabetes is a problem that is lifestyle related. It is our sedentary society with an overabundance of food. Doesn't mean that the food's nutritious. It just means we have too much food, and when you have too many calories in and not enough calories out, you become overweight and obese. And it is this obesity factor that plays a very, very big role in type 2 diabetes. And the reason it plays a very, very big role is because fat cells produce a chemical that blocks insulin receptor activity. So that's why this is a very big problem for our society right now. So this is due to, we'll say, non-responsive insulin receptors. Or another word we can use is insulin receptor dysfunction. Due to a chemical produced and released by adipocytes. So with this problem, with the obesity and this chemical blocking insulin receptors, we no longer have glucose entry into our cells, right? Because we need insulin receptor activity to be proper in order for glucose to go into the cell. So these insulin receptors are now being interfered with, so we have dysfunctionality of our insulin receptors, and this will cause our blood glucose levels to go up. Well, if the blood glucose levels are going up, let me ask you too, what do you know about insulin levels for these people? It's not, so that's a reasonable thought. That's a reasonable thought. But if glucose, what is the stimulus for insulin release, people? High blood glucose. With type 1 diabetes, we know what about insulin? It's not there. With type 2 diabetes, we didn't say insulin wasn't there, did we? We said insulin doesn't work. So high blood glucose means high insulin levels. So these two, can you guys see, these are two very, very different problems here. They cause the same effect, but two very different problems. So this chemical released by the fat cells, which are causing insulin receptor dysfunction, is causing elevated blood glucose levels as well as elevated insulin levels, because that's what you do. When you have high blood glucose, you release more insulin. So don't forget that this process is due to this diabetes. These two diabetes are due to two very different types of processes here. So with this group, we do have high blood glucose, but you also have high insulin levels. And the other thing is ketosis, or this ketone issue and ketoacidosis, is usually not a problem. Because your cells are still able to get some glucose in. So remember, it's this chemical that's messing with the insulin receptors, but not all insulin receptors are always being messed with at the same time. So you do get some glucose into your cells. And so the blood glucose level definitely creeps up and creeps up and creeps up, and it takes a long time for this type 2 diabetes to be present for it to cause you to have a problem such as ketoacidosis. What's the treatment? TX is abbreviation for treatment. What do you know already is the normal treatment for type 2 diabetes? Diet and exercise. Absolutely, still. And what else should be part of treatment for type 2 diabetes?
I was going to ask about that. Metformin, like any sort of medications, what does metformin do?
Metformin helps with the insulin receptor interference. So that's why it works. But the other thing, if you don't want to do the medication route, the next thing you need to do is get rid of that chemical, right? That is interfering. And the only way you can do that is by weight loss. You know, it's really interesting. You can get people to diet and exercise more readily if you don't tell them they need to lose weight. But weight loss is actually quite key to this, correct? And that's what diet and exercise are supposed to do. They're supposed to bring out that weight loss process. So we'll stop there. Sorry I got into the diabetes story a little bit. And give you a couple clickers.